Okay, in today's class we will mostly talk about scheme theory or affine schemes mostly. But before that, a short introduction to why these schemes are important. Okay, so this theory of schemes, this was originally due to Grothendieck. So he invented this idea of schemes, studying geometry, algebraic geometry in scheme theoretic way. This is his foundation of algebraic geometry. So this was done by started by Grothendieck, Alexander Grothendieck. So the idea was to make it make everything functorial. The first motivation to study. So motivation to so this helps you to study. So it is more functorial. So functorial in the sense that if you, so for example, if you have a ring homomorphism A to B, then if you know that, just see, so far we have seen for key algebras, right? But when you talk about varieties, then the ring which you deal with is the K algebra, which is a finitely generated K algebra reduced. So, but what was his idea is that you don't work. So, this is a very restrictive category in the category of rings. He was interested in giving a topological space structure on for any ring. So that you can do naturally if you take this map, the functor spec functor, which is a contravariant functor. So spec B to spec A. That if you start with a ring homomorphism, everything is commutative. All rings are commutative with all rings are commutative with identity. So then this you have this map phi star, say spec B. So this is P goes to P contraction. But you know that if you are in the category of so in the category of variety, what you took the maximal ideals of rings, right? Then, and if K is algebraically closed, finitely generated algebra, then you have some correspondence. The points goes to points. But here the point, for example, the particular example, you take that Z goes to, you take the Z inclusion in Q. Here you see the 0 is not a maximal ideal. So if you take spec of Q, which is only one element, which is basically the 0 ideal, but 0 is not a maximal ideal. So maximal ideal does not go to maximal ideal. So functoriality gets lost if you work with maximal ideals. But if you take this P contraction means phi inverse of P. But if you take the prime ideals, then there is a natural map, and also you can recover the map phi from this. If you have a map from spec B to spec A, you can recover back your ring homomorphism. It is always any, I mean, not any map, but some you have to put some topology. But anyway, that will come to. But this is true that if you can put a topology on this space, this set of all prime ideals, and if you have a continuous map, then any continuous map actually comes from the ring homomorphism. So this is also first one is that this spec functor, this spec is a good spec is a contravariant functor. So this is one way, one reason to do scheme. This is more functorial. Another reason is that here you can talk about spec Z, but this guy is a non-finite type. It's not a, if you take, so this is not a, how, I mean, it has, it's a non-finite type object. I mean, so that means it's not a finitely generated algebra, or it's a non-finite. And so, or what I say, I mean, see here the, for example, primes, right? Primes are inside this spec of Z. So, in particular, so what you do in some sense, that if you define something over spec Z, then there is a natural map to spec Z to, if you take the residue field, so spec of Fp, or so there are some advantages if you work with spec Z, because if you work with any abelian, any commutative ring, then you can think that that is always a Z module. That means there is some homomorphism from Z to R, right? There is always a ring homomorphism. So, spec R to spec Z, there is always a map, natural map. So, everything, so you can define everything over spec Z. So, any scheme, if it is defined, suppose, so when you define some system of equation over a field, right? Like you have some system of equation, right? Say f alpha x y, where these f alphas are, these are elements in some field. But instead of, and you are, when you are looking at solution, you are looking at solution in some k A2, and A2 is the field, but instead of field k, you could take some any ring. For example, if you are interested in some solution, something, some equation like x square plus 3y square equal to say 5. You may be interested not in the field, not in field q, but you are interested in solution in some z. It's integer solution. That makes sense. Integer solution of an equation. Then what you do? Then it has to be the, so you define it over z, and then you look for solution over z. So, this kind of thing appears in number theory exam, I mean, especially that this kind of geometrical object, this will give you a scheme structure. So, but this is our spec Z. So, it is not a finite type scheme in some sense. So, it is defined over spec Z. Spec Z is not a finite type. It is not a finitely generated algebra. So, this is an advantage, that you can mix number theoretic concept here. Another reason is that in that this A can be any ring. A can have nilpotents. That means it may be non-reduced. In the case of varieties, we saw that the finite, the coordinate ring, they don't have they are reduced. So, you lose some information. So, this is much more general, that you can include such. So, for example, such function like x power n. You can have a function x as the x power n equal to 0, but x is not 0, right? Because the element of ring gives you some kind of functions on some space. So, in this case, the space is spec A, and the function space is A. We will see that, how you see. And another important thing, that this scheme theory, there is concept of generic point. See, in the case of varieties, the points, they are close point because it corresponds to maximal ideal. Every point, if you take the closure, then they are there itself. But in schemes, there are non-closed points. That means that if you take the closure of a point, it need not be the point. It may be something bigger than that point. So that is called generic points. So concept of generic points is, for example, if you consider spec of Z. So these are prime ideas, right? So if I write spec of Z as this, then every prime, say 2, 2, 3, 5, dot dot dot, all primes are here. These are close point because they correspond to maximal ideal. I'll talk about what is a topology and all, but I'm just giving a hint that why. But you have this point 0, which is like a big point. It's not just one point, because this is also a point in spec Z, but this is not a closed point. Because if you take the closure, what will you get? The entire space. So it's a fat point or dense. A point is actually a dense open subset. So this concept is very important, that that you have some concept of generic point. Actually, in spec A, every closed subset has such point. Every closed subset or irreducible closed subset has such point. One point is there, which is the generic point. Yes, for anything. So this concept of generic points, which is very important in, which is kind of so this is plays. I mean, for example, if you want to do some study over non-algebraically closed field, these concepts, these generic points plays a very important role. Okay. So these are kind of short motivation that why one should study schemes, because you are broadening your the space. I mean, not just finitely generated K algebra reduce, but you include, once you include Z, you can do arithmetic, right? That was his motivation to. I mean, you should include Z. Okay. Okay. So now let's start with this. So spec A. So let's define that. So spectrum of a ring. So A, as usual, commutative with identity. Commutative ring with identity. Then spec A as the set is a set of all prime ideals. Prime. So when I say prime ideal, I don't include the entire ring A. So it's a proper prime ideal. Say a point, generally I will denote it by X, and the corresponding prime ideal I denote it by Px. So Px, a point corresponds to a prime ideal, that I write it as Px. But when I write point in spec A, I write it as X, a point. So, but the point, so for every X, you can construct a field, which is called residue field. You consider the localization A of Px. Px is a prime ideal, and consider it is a local ring, and the maximal ideal is the ideal generated by Px. Take the quotient. So this you call it kx. Right. So this is called residue field at x. X may be any point, need not be closed point. It may be a non-closed point. For every point in space A, you can define such. So now, so once you have such so now you can define a map A to A of or kx. For every x, you can define a map, sorry, kx. Right, because you take the element f, you go to, it will give you element in APX because there is a natural map, localization map, and then you are quotienting by this ideal. So so f is, so you call that f of x, and this f of x is an element in kx. This k has nothing to do with any field. This is just a notation. Huh? F by 1 bar, yes. But you see that for different x, if I take another prime x prime, this kx and kx prime are different. When k was algebraically closed field, this would have been same. But if k is not algebraically closed field, these residue fields will be different. So it will be some extensions of k. If A is a k finitely generated k algebra. If A is a finitely generated k algebra, then this residue field will be extension of k, some finite extensions. So then, so for every, so the point, so this is a remark that if x prime not equal to x, means this kx and kx prime may be different. Kx's are different and they are different field. Or that's right. Different at different points. So the evaluation. So this is the first kx's are different in general, which is very much different from the but when you define a function in the variety case, it was like to a fixed field, right? When you start with the variety x, then you consider ax. So ax is like a function to a fixed field k. But here it is not to a fixed field. It is in the residue field for every point. So if you start if x is your spec of A, so Ax is basically the functions on X. So the ring which you start with actually is a function space on spec A. So you can think like that. So every point of the ring, it is actually a function on spec A, because so to define a function, that means for every x I should associate some value, right? So that is f of x. But this f of x takes values in their different field, not just in one field. So in some sense, it is if you take the disjoint union of k, x belongs to spec A. So now A can be thought of as functions from your spec A to this. For every x, it goes to it takes values at kx. Depends on the point. Where it takes values, it depends on the in the case of variety, it was fixed. It was taking value in a fixed field. But now the functions, they are not in the fixed field. It is on a different field. Depends on the point. For every point in A, yes. I mean, you think always the ring is the function space and the objects are the spectrum of the function space. As you have seen that in the even variety, functions are more important, right? At the level of sets, they are same, but it may not be isomorphic as varieties. The bijection does not give you a isomorphism of variety. So, there is a functions are important, that gives you the structure. So, sometimes this is notation is evaluation at x. You are taking any function and then you are taking evaluation of x at f.